Yes, there is another type of weathering, biochemical weathering, where plant roots, fungi, and lichens secrete organic acids that help dissolve minerals in rocks and extract nutrients from the minerals. So that it would be an example of biochemical weathering. Now, as I was mentioning earlier, physical and chemical weathering work together. Now you see a feldspar rock here that has some feldspar, so that's like that pink mineral that we saw in the last presentation. Quartz, that is silicon and oxygen together. Biotite, so that's a form of dark black mica. So we are looking here at an intact rock. And so chemical weathering weakens the rock and breaks it apart. And then the increase in surface area from breaking the rock apart allows the chemical reactions and chemical weathering to happen faster, just like that example of the cube you're seeing up there. So in the example, it shows the surface area of the cube is 6 square meters. So then what happens if you break the cube up into 8 smaller cubes? So now you don't just have those 6 faces, you have 6 times 4 faces exposed. So that's more surface area exposed, where there can be more reactions occurring. It can be exposed to, just think like an easy example would be thinking about that iron-rich rock. You break it apart, and then that part that would have been that center part that wasn't previously exposed to oxygen becomes exposed to oxygen all over the place, and it rusts quicker. So here the example would be increasing the surface area now to 12 square meters. Then you break it into lots of itty bitty cubes, and now you have more cracks, more surface area. So here we're, for example, increasing the surface area to 60 square meters. So then the chemical weathering and the physical weathering speed up. They help each other along. So over time, that rock we were talking about earlier has broken into loose grains. The feldspar has turned to clay, which is really easy to break apart. And then eventually it gets carried away via a fluid. So that would be erosion. Now, in the concept and vocabulary sheet that I posted, you'll see a little bit about sediment texture. So sediment texture has to do with the size and shape of the sediments. So let's start with particle size. So boulders are classified as greater than 256 millimeters in diameter. Cobbles are between 64 and 256 millimeters in diameter. Pebbles are between 2 millimeters and 64 millimeters in diameter. Then sand is between 1/16 of a millimeter and 2 millimeters. Silt is between 1/256 millimeters and 1/16 millimeter. And clay is less than 1/256 millimeter. So clay is the finest, right? Silt, the texture of silt is very similar to that as flour that you bake with. And we all have a basic sense of what sand feels like. It's kind of coarse and gritty. Clay is actually a little bit flat and platy, but we won't worry too much about that at the moment. Now let's look a little bit at angularity. So when you have broken up, really angular, jagged clasts, guess what? We call that angular. So sometimes terms in geology, sedimentology, soils are exactly what they sound like. Then subangular is a little more rounded. Subrounded is more rounded than that, and rounded is completely smooth and rounded. Now, if we're looking at rocks here, both examples below would be sedimentary rocks. The one on the left with the really angular, sharp pieces, the sharp clasts in it, would be called a breccia. The one on the right with the really smooth pebbles in it would be called a conglomerate. And the reason that they look different is in part due to which sort of environment they were transported in and deposited in. And so now we're going to look at that. But first, the type of weathering is also a function of the climatic conditions. So say you get a lot of rain and it's pretty cold climate conditions. You get more mechanical weathering. Then if you get warmer conditions, you get more chemical weathering. So to spend a little bit of time with that figure if you'd like, and try to think about your own interpretation of it and whether or not it makes sense to you. Now, I know there is a lot going on here. So let's talk about erosion. So erosion is fluid, air, or water movement, removes soil, rock, debris, or dissolved material from a surface. And this happens via physical processes. So that could be precipitation, different than... So this is the precipitation, like rain falling out of the sky. So precipitation, surface runoff. So there's different types of runoff from rain. There's splash, sheet, rill, and gully are different types of erosion. We get rivers and streams do some down cutting based on their energy. So streams are highly energetic. You have lots of water moving along. And so you get down cutting. You also get cutting into the banks. Coastal, you get hydraulic action. So you get some wave pounding and scouring, because remember, ocean water is salty, so it's like sandpaper. It's really good at scouring away rock. So pounding, abrasion, corrosion, because there's carbonic acids. There's also some suspended and dissolved rocks in there too, so it's very effective. We get attrition, those particles, sea load carried by waves, worn down as they hit each other, and cliffs. You can also get bioerosion, so you can get materials carried away by animals, right? Then we have some chemical erosion, so that's loss of matter in the landscape in the form of solutes. Glaciers, you get abrasion, scouring, plucking, ice thrusting, and we'll go through a little bit some examples with this. Floods, you get large volumes of turbulent water. Wind erosion, you get abrasion and deflation. And mass movements, so landslides are another way you get erosion. And some functions, some factors that we like to think about are climate, vegetation, topography, and tectonics are the factors to consider here. So just one more time, weathering and erosion, they work together. They're not the same thing. Weathering is the process that breaks down a rock. Erosion lifts away the rock. Now here's some examples of water erosion. Here we have a desert on top. And actually, in many desert environments, a lot of the different landscape features that you see were carved away by floods, massive flooding. So you can actually see where the water would have traveled here. And in the Bill Nye video, he shows you erosion in action like this. And then you can also get erosion in glacial environments from really fast moving meltwater, just wearing away the banks and the rocks surrounding it. And here's an example of coastal landforms that you get from erosion. So you can get here, sea arch is an example. You can get some caves, different notches, so take a close look at those. And now here's an example of how glaciers transform and erode an environment. So here is an example of a landscape before glaciation. Then the glaciers come, and when they retreat, they have carved out the landscape. Next we have desert erosion, so we just saw that ice can erode, so we went through water, we went through ice, and now we're on wind. Wind can pick up materials and erode away the landscape as well. So this is an example of erosion over time, and on the bottom it shows we have cracks and jointing, and we've got an erosion in that landscape and just what it can look like in a desert type dry environment where a lot of the time there's not much water, and so we get wind erosion. Now we started with weathering. Erosion lifts away the particles, and then via the fluid medium we get some transport. Now let's start with water. I feel that water is the easiest to visualize, so you can get different loads. We have a dissolved load, so these are ions of dissolved minerals from soluble minerals in sediment or rock and or from groundwater seepage. Then you have a suspended load, so these are tiny solid grains. So remember our finer textured particles like silt or clay, it's easier, they're smaller, they're finer, so they stay suspended in water for longer, so they're carried by water without settling down, especially when water's in motion. It requires a still environment for clay to settle out fully, like a pond or a lake that's very, very still. It's not going to, clay isn't really going to settle out in a moving river. Bed load, that's the large particles, sand, pebbles, cobbles that bounce or roll around the stream floor. So that would be called saltation, when you get these sort of bouncing particles that go along and they're moving in the same direction as flow. And so when you think back to that conglomerate rock that we saw a few slides ago with the really rounded pebbles, well, pebbles become rounded when they roll along the stream floor. And so that's showing that it likely came from a riverine environment, that rock. Now, this is a bit of a complicated graph. It's showing the relationship between particle size and flow velocity, and whether the particles will be transported, eroded, or deposited. So let's start down to the left where we have clay. We have fine particles down by the left here. And the flow velocity is slowest down at the bottom of this y-axis, and it is fastest at the top, and this is a log base 10 scale, so we're going up by factors of 10, increasing. So when you have slow flowing water, so not a lot of energy, you get transport of fine particles because it doesn't take a lot of energy to keep the fine particles suspended. So then let's move on forward a little bit more, and you see how this gray transportation shaded area gets smaller and smaller and smaller, because the larger the particles you have, the more energy it takes to transport them. But then when you get really energetic water, so these really high velocity water up here, you're going to get wearing away and erosion of the particles rather than transport. And then if you have slower, less energetic water and larger particles, they're not even going to be lifted at all. They're just going to be, they're going to fall out of the water. They're going to be deposited. And here is an example of glacial transport, so being transported by a glacier. And it works in a similar way to a conveyor belt. So you have ice that is melting. So retreating, so the max extent would be going this way, but ice is still flowing down to the left here. And with it, it's carrying bits of debris and it's depositing them in something called a moraine. And so when you get a moraine, you get poorly sorted sediments. So unlike with a river, which really depended on the velocity of the water, and then you can get you get good sorting there because particles that are too big to stay suspended settle out. Here, everything's just getting dropped at the toe of the glacier. And so we get this unsorted marine with some of these angular clasts and all a mess of different things. So, no, go back. So let's just look briefly at moraines. Moraines are a pile of sediment carried or left behind by a glacier. So a lateral moraine is dropped on the side margins of a glacier. So that would be these out on the sides here. Medial moraines are dropped down the interior. And ground moraine is left at the base. All right, end moraine is accumulation of sediment transported to a glacier's toe. And terminal moraine is the end moraine at the furthest limit of glaciation. So that's where so to the furthest extent where the glacier reached. So you won't see any more moraine piled beyond this point. That's why it's the terminal one. It's the last one that you see. Okay, getting there. We're moving on to wind. So much like you see in water, you get some really fine silts and clays, we call it loess, suspended in the air and transported that way. And then some of the coarser sand rolls and bounces around on the ground. So once again, we get a suspended or dust load, and then we get the surface load, which is called saltating. And deposition in a desert environment really depends on the direction of wind. This schematic shows the formation of different types of sand dunes based on wind patterns. And finally, looking at this image from Geology Cafe, this is just a broad overview of different types of depositional environments. We get an abyssal fan out here, so where we have fast moving water that empties out to the very still deepest depths of the ocean. We get the continental shelf, so that's the more shallow part of the ocean. And you see the alluvial fan here, so that would happen in a desert when there's a flood and then it dries back out. A playa, that's an ephemeral lake, so that means it's there part-time, not all year long. Perennial means it's there all the time. All right, and you can see the river and some dunes that were settled out that were deposited via the wind.